Hello, welcome to another video about the motion of charged particles in a magnetic field. This particular video is about circular motion of charged particles. A charged particle moving at right angles to a uniform magnetic field experiences a force of constant magnitude at right angles to the velocity. The force changes the direction, but not the speed of the charged particle, and hence the particle moves with the uniform circular motion. In stage 2 physics, you'll need to be able to explain how the velocity dependence of the magnetic force on a charged particle causes the particle to move with uniform circular motion when it enters a uniform magnetic field at right angles. You'll also need to be able to derive this equation here for the radius of a circular path of an ion with a charge and a mass that is moving with a speed at right angles to a uniform magnetic field. You'll also need to be able to solve problems involving the use of said equation. So, as we have just touched on, charged particles with a velocity perpendicular to a uniform magnetic field will experience a force that is perpendicular to their velocity. So perpendicular means at a right angle. With this, my suggestion is to just verify it for yourself using the right hand palm rule. So if you imagine, pick one of the points on this circle here, this circular path of motion where the green arrow signifies velocity, point your thumb in that direction and then point your fingers into the page because that's the direction of the magnetic field. And you'll notice that this must be a negatively charged particle, that the force is always going to be perpendicular to the direction of the velocity. The reason that I say this particle must be negatively charged is because the force is coming out of the back of your right hand, and that happens with negative charges. I've just noticed that the Q here is negative. I didn't see that before, so all good, it checks out. The perpendicular force changes the direction of the particle without changing the speed. So this is exactly like circular motion. A perpendicular force to an object that's travelling in a circle will provide the centripetal acceleration for that object's motion. So if you think about like totem tennis, or just even cast your mind back to circular motion last term, this is the same thing that's happening. It's just this time around the force is provided by a magnetic field. So to derive the radius of a charged particle's circular path, so the formula for this, we need to assume that the magnetic force causes the centripetal acceleration of the charge moving perpendicular to the uniform magnetic field B, which is what we were just discussing on the previous slide. So when we're assuming this, we're saying that the force, which is this rule here, in the previous video we were looking at force being equal to this multiplied by sine of the angle. Because the charge is moving perpendicular, sine 90 is equal to 1, so we don't have to worry about putting or including this part. So we're saying that this force, I'll just say that that's force over there. I'd encourage you to write these notes down as you're watching. We're saying that the magnetic force is equal to the centripetal force, which we know is equal to mass times velocity squared on r, which is our centripetal force equation. Then from there, we can see that there's a v squared over here and a v over here, so velocity squared and velocity, so these will cancel out. The v's won't cancel, as in they won't disappear, but the v on the left-hand side of the equation will, and the squared will disappear because there's one v on the left-hand side, there's v squared or two v's multiplying by each other on the right-hand side. So this will simplify to QB, or charge times magnetic field, is equal to mass times velocity divided by radius. To get radius by itself, which is what we're looking for, we just need to multiply both sides by the radius, so times by r times by r. These r's will cancel out and we'll be left with r multiplied by charge, or radius multiplied by charge multiplied by magnetic field, is equal to mass times velocity. And then our final step is to divide both sides by QB. These QB's will cancel and we'll be left with radius is equal to mass times velocity divided by charge multiplied by the magnetic field strength. And that is how you derive that equation. Just to note, radius is equal to, or radius is measured in meters. The mass is measured in kilograms. The velocity is measured in meters per second. Maybe I'll put equal sign for all of them now. The charge is measured in coulombs, and the magnetic field strength is measured in Teslas. So as an example, we've got an electron moving to the left with a velocity of 1.8 by 10 to the 7 meters per second, and it's entering perpendicularly to a 6 megatesla magnetic field, which is directed out of the page, and I've drawn a little diagram there to show this. What is the radius and direction of the electron's path? So we'll just use the rule that we derived. So radius is equal to mass of the particle multiplied by the velocity of the particle divided by the charge of the particle and by the magnetic field strength. Our velocity is equal to 1.8 by 10 to the 7 meters per second. The mass of an electron, this will be on your formula sheet, is equal to 9.11 by 10 to the negative 31 kilograms. The magnetic field strength is equal to 6 megateslas, which is 6 by 10 to the 6 teslas. And the charge of an electron, also included on your formula sheet, is 1.6 by 10 to the negative 19. The charge on an electron is obviously negative in this situation. We just need to focus on the magnitude. So the radius will be equal to, I wonder if I'll be able to fit this in. I probably won't be, so I'm going to start again a bit lower down. So to the left, the radius is going to be equal to the mass, which is 9.11 by 10 to the negative 31, multiplied by 1.8 by 10 to the 7, which is the velocity of the electron. The charge on the electron is 1.6 by 10 to the negative 19 coulombs, and the magnetic field strength is 6 by 10 to the 6 teslas. If you pop all of this into your calculator, you'll end up with a radius of 1.7 by 10 to the negative 11 meters, so quite a small circle. Now, the other thing that I asked was, what is the direction of the electron's path? So to work this out, we'll use our right hand rule, and we have to remember to reverse the direction of the charge because we're working with a negative electron here. So we'll point our thumb to the left, which is in the direction of the velocity. We'll point our fingers out of the page, and our palm should be pushing away from us. But because it's a negative charge, will take the direction of the force to come out of the back of our hand, so it will be towards us. So if this force is acting on the velocity, we can imagine that the velocity will start to move, or the particle's motion will start to move in an anti-clockwise direction. So this circular motion will be anti-clockwise.